Okay, so yeah, my name is Raul Gracia. I'm a software engineer in the Pravega team for 3 years now. I'm going to, go over the performance of Pravega under parallel workloads, which has been one of the main focus of work for the '09 release. So this will be the outline of the presentation. We'll just briefly mention what's new in Pravega '09 in terms of performance. Then I will briefly go over the experimental setup for the experiments that we are going to see in the results section, and then I will just wrap up. So what has been new in Pravega '09 in terms of performance, right? So our goal has been to basically improve the data ingestion performance for those scenarios in which there is a high degree of parallelism, meaning that there are many writers, dozens, or and writing to thousands of segments, right? This could be a plausible scenario in edge or IoT workloads. So we targeted that one. You can see here a few of the main contributions. This is not an exhaustive list, but there are a few of them of the pull requests that greatly improve the performance of Pravega in those situations for those workloads. And basically, what we achieved in Pravega '09 is that Pravega now has a better throughput when dealing with many writers and segments in parallel. It provides also a lower write latency, especially with working with connection pooling. Just for those that do not know what connection pooling is basically a feature in the Pravega writer that basically multiplexes the writes for multiple segments for a given segment store, right? So in this particular case, which really fits the kind of scenarios we are evaluating here, we had a very significant improvement in write latency. Also, Pravega is more stable under highly parallel workloads, and it consumes a lower amount of CPU. So all those achievements, we are going to go over the main results that we have in an evaluation we did doing experiments on Amazon. So I mean the full report, you can see that in the blog post that we published 1 month ago. But in this talk, we are going to go over overview some of the results. So let's start with the experimental setup we used to do the performance comparison, right? So basically, in most of the experiments we have in that blog post, you will see that we basically fixed the incoming throughput, right? In this case to 250 megabytes per second using 1 kilobyte events, right? And what we change as knobs is the number of producers or writers and consumers as well, and the number of segments, right? So we fix the throughput and basically change the parallelism of the same workload to see the impact of that in the different systems, right? Another important point is that we used routing keys, basically chosen at random when writing data to the storage systems. And of course, we compare Pravega against the same workload for Kafka and Pulsar, right? In the table in the right side, you can see, in detail what are the main settings we used for this comparison. But a few of the main points we have to take into account is that we use the same replication scheme for all the systems, 3 replicas, and waiting for 2 acknowledgements per write. And also the kind of instances that we used, right? So we did the experiments on Amazon, so we used, to emulate this kind of highly parallel workloads, 10 VMs for running Open Messaging Benchmark, which is the tool that we use to execute our experiments, right? We had in all the cases 3 server instances, and in all cases as well, we use a single NVMe drive for journaling, right? So that being said, let's go over the results, right? We are going to focus on both throughput and latency. So let's start with throughput, right? So in this comparison, you can see in this plot that Pravega can achieve the 250 megabytes per second, right? In basically, irrespective of the number of producers and number of segments, right? You can see the blue lines on top of the 250 megabytes per second target rate all the time. But this is not the case for Kafka, right? So what we observed is that there is a point as soon as we add more partitions to the Kafka producer, we see that the throughput rate that we can get goes lower. This can be mitigated by adding more producers, right? So you can see that for 100 producers, we get higher throughput compared to with 10 producers, but still there is an upper bound to this improvement, right? And this is for the gray lines that you can see in Kafka, which is the default mode in which it does not flushes each write to the drive before acknowledging. We also compared, with Kafka when configured to flashing each and every message to the drive before acknowledging, which is the ping lines, right? So you can see there that adding this durability guarantee to Kafka really induces a very high penalty in terms of throughput, right? If we compare with Pulsar, one of the things that we observe with Pulsar is that with the configurations that we define for as a default for all those experiments, we got a very unstable behavior, right, from Pulsar. Actually, we observed that when writing with many writers and using many segments in parallel, using acknowledgement quorum 2 induced frequent out-of-memory on bookies, right? And this, couldn't, allow us to complete the full set of experiments that we are showing here. The other thing is that using routing keys, we observed also very often problems between bookies and Pulsar brokers. Basically, what we observed is an operation rejected error, right? That if you go, it boils down to be the DB ledger, which is the ledger that is configured by default in Pulsar. The DB ledger not being able to keep up with the amount of writes to the journal, right? So for this reason, you can see that Pulsar, which are the red lines in this plot, you can see that in this case, almost none of them could make it more than for 100 segments, right? So what we did to see what the problem was is to use a more favorable configuration for Pulsar, right? So instead of using acknowledgement quorum 2, we use acknowledgement quorum 3, right? So this basically reduced the amount of out-of-memory issues we observe in Pulsar, and also we, configure the benchmark to do not use routing keys instead of using them at random, right? This ideally would improve the capacity of the client to batch writes and make a more efficient, writing to the server. This favorable configuration, you can see that in the yellow line. And for example, for the 10 producer case, we could get also the 250 megabytes per second in all the cases. But again, for the 100 producer case, we observe also crashes at 1,000 segments, right? So yes, we observe a much better behavior for Pulsar when changing those settings, but still is not fully stable, right? Which also has an implication, right? Because not using routing keys, the fact of that having an improvement means that writing in parallel to all the partitions, it's a difficult scenario for Pulsar, right? And the other metric we are going to focus is latency. So if we compare that with the latency between Pravega and Kafka, we can see that Pravega provides a much better latency for the 95 percentile write latency compared to Kafka, right? So we can see that the difference goes, is increased as we add the number of partitions to Kafka. And in the case of Pravega, we can see that in almost all the cases, perhaps with the exception of the 100 producers and 5,000 segments, in all cases we can achieve a single-digit millisecond P95 write latency, right? Which is very interesting. And yeah, also to mention that the fact of adding durability in Kafka again shows a significant increase in in terms of latency. Yeah, with Pulsar, again, we have the issue of the instability when using the default configuration compared to the other systems. So if we compare the favorable configuration, we see that with 10 producers, Pulsar provides a similar or even better P95 write latency compared to Pravega, right? But if we again go to the 100 producers case, we see that the write latency starts climbing until the system becomes instable and stops working, right? So yeah, that's the summary of the results. And just as a wrap up, so we have done tons of work in Pravega 09 to improve performance under parallel workloads. We also observed that Pravega provides better results than Kafka and Pulsar in most cases. And of course, if you want to see the full details on the comparison, the code we used, and all that set of details, please read the blog post. And of course, if you have any doubt, ask in the Slack channel. And yeah, stay tuned for new updates in performance. So yeah, you have any question?
Where do we go from here in terms of performance, or maybe even future evaluations? Do you have an idea of that?
Yeah, there are many open fronts here, right? So at least what we are evaluating now is the read performance, right? So we have been working on the write path for, I don't know, 1 year so far. But now what we are, being interested in improving is to evaluate the read path, because in some situations when dealing with, thousands of segments and very small events, we see that readers are not as efficient as writers. There are reasons for that, right? The kind of contract that the Pravega reader provides. But still, we are trying to improve, especially the read side at this point, and there is work to do there. Of course, there are other things that are also very critical, including transactions, and yeah. So, and I am aware that, for example, Andre is also working on on the performance of the KW store. So yeah, many open fronts in that. So we are not going to get bored here.